We have already studied about the fundamentals of quantum mechanics, and we have seen that quantum mechanics is basically a theoretical science of microscopic matter, and it operates through time independent Schrodinger equation for conservative systems. We have also seen that whenever we have to do a quantum mechanical study of any system, there are 4 steps which one has to follow. And these 4 steps are writing Schrodinger equation, defining boundary conditions, solving Schrodinger equation, and lastly, extracting information out of the wave function. So, in this module today, we will discuss the application of time independent Schrodinger equation to a simplest case, and the simplest case is particle in a one-dimensional box. Now, why do we study this system? Because particle in a one-dimensional box is a very simple case of translational motion of the particle. A single particle can have only translational energy. Therefore, it will be a model for translational energy. Now, how to start it? First of all, we will define our model. We are assuming that the particle is of mass m and it is moving in a one-dimensional box, and that dimension is along x direction. The length of the box is L. That means you can see on one extreme is x is equal to 0, and on the other extreme it is x is equal to L. So, the particle is inside this box, and then the walls of this box are infinitely large, and we also assume that the potential energy of this particle inside the box is 0. So, these are the assumptions of our model. Now, if we have to carry out quantum mechanical study of this particle, first of all, we will have to define Schrodinger equation for this particle. Defining Schrodinger equation, as you know, is h cap psi is equal to E psi. We have to define h cap, which is the Hamiltonian for this particle. Hamiltonian is made up of kinetic energy operator T cap and potential energy operator V cap. Since we are assuming potential energy to be 0, therefore V cap will be 0. But the corresponding kinetic energy operator T cap, as we have learnt already, is equal to minus h square upon 8 pi square m d2 by dx2. So, if we substitute this value in this Schrodinger equation, we get the resulting equation, which is d2 psi x upon dx2 plus 8 pi square m upon h square E psi x is equal to 0. And if all this quantity, second term, we make a substitution and define k square, then this equation becomes d2 psi x upon dx2 plus k square psi x is equal to 0. So, that is the Schrodinger equation for a particle in one-dimensional box. Second step is defining the boundary conditions. As you already know, the length of the box is L, and one end we have x is equal to 0, and on the other hand we have x is equal to L. And at these two boundaries, wave function must be 0, because particle cannot exist outside these two extremes. So, at x is equal to 0, psi is 0, and at x is equal to L, psi is 0. These are the two boundary conditions. After having defined boundary conditions, our next step is to solve the Schrodinger equation. And as you can see, this is a simple differential equation d2 psi upon dx2 plus k square psi is equal to 0. For this equation, the general solution is psi x is equal to a sine kx plus b cos kx. This is the general solution for this partial second order differential equation. Now if we apply boundary conditions one by one, suppose we put x is equal to 0 and at this psi is equal to 0, then by applying this boundary condition we get b is equal to 0. Similarly, if we apply the second boundary condition, which is that when x is equal to L, psi would be equal to again 0, then this gives rise to the condition sin kl is equal to sin n pi, and that means k is equal to n pi by 2. So this becomes the result of the second boundary condition. But we know that k square is equal to 8 pi square me upon h square, and if we put it back from here, we straightway get energy of the particle En, which is equal to n square h square upon 8ml square. Here n can have the value of 1, 2, 3, etc. But please remember, n cannot have the value equal to 0. After finding out the energy, our wave function becomes psi nx is equal to a sin n pi x upon L. Now we need to determine the value of a, and we know it very well, and that can be done through normalization condition, because within the box the total probability has to be equal to 1. And if we apply normalization condition here, we find that ultimately a comes out to be equal to 2 by L under root. After having found out the value of a, now we get the final wave function for this particle, and that is psi nx is equal to 2 by L under root sin n pi x upon L. You can see here the wave function will vary with the value of n, and it will also vary with the value of x. These two are very important things. Since we have found that for this particle, the total energy, which is the translational energy, is given by h square upon 8ml square, we can see here these are the corresponding energy levels. The ground state will be one which will correspond to n is equal to 1, then next state will be n is equal to 2. So in this way we can get the various energy levels. Please remember that n is equal to 0 is not allowed, because if n would be 0, then the translational energy of the particle will be 0, and that's not possible, because particle is confined in a box, and if its energy or if its kinetic energy is 0, then it will violate Heisenberg uncertainty principle. Since we have also found out the corresponding wave function, here we can also show how the wave functions will vary. We have already learned earlier that wave function is probability amplitude, and the wave function square or wave function into wave function complex conjugate, which has to be a real quantity, is the probability density. So in this figure we have the plots of the wave function as well as plots of the probability density. You can see in the left hand side for the ground state how the wave function looks. Then for n is equal to 2, there is one node in the middle of the box, and in n is equal to 3, there are two nodes. But when we plot the corresponding probability density, which is the square of this wave function, these all become positive, and that is represented on the right hand side. One thing which is very obvious, that in the plot you can say, if you are making a plot of the wave function for nth state, it will have n minus 1 nodes. Just as you see in n is equal to 3, there are two nodes. Now one thing is very clear here, that as n increases, energy increases, wave function changes, and one thing more which is important is that wave function is independent of the mass of the particle. Wave function depends only on the length of the box. In this figure you can see that as the value of n increases, the probability density distribution becomes more and more uniform. You can see that at very high values of n, there will be many maxima. So that means for n being very, very large, the distribution or probability distribution of the particle inside the box will become more or less uniform. This is very, very important. One must also remember that these wave functions which we have found out from the solution of the Schrodinger equations, these form an orthonormal set. That means each wave function in itself is normalized and each wave function is orthogonal to every other wave function. So this is very, very important point. This we denote in the form of integral. You can see integral psi m star psi n d tau is delta mn. Delta mn would be 1 if m is equal to n. This is the normalization condition. And if m is not equal to n, this would be equal to 0. So these wave functions form an orthonormal set. Sometimes one asks, what are the units of the wave functions? Since the wave function is given by the expression 2 by L under root sine n pi x upon L. Now, sine has no unit. So, the units would be only of 2 by L under root, that is L minus half. That would be the corresponding units of the length. That means distance square root 1 upon reciprocal minus of that. So now you see that we have studied the particle in a one-dimensional box problem. We have got the wave function, we have got the energy, we find that the energy is quantized, we find that the wave function, how it looks, how it is represented, and how does the corresponding probability density distribution looks. After having done this, one may ask a question that what would happen if the particle is moving instead of one-dimensional box in a two-dimensional box or a three-dimensional box. That's quite common. So how will quantum mechanical treatment treat such a problem? So now we will take the case of a particle in a three-dimensional box. Here we have the particle of mass m again in the box, but it is three-dimensional along x, along y, along z. Along x direction, its length is a. Along y direction, its length is b. And along z direction, its length is c. For such a particle, therefore, the boundary conditions become very obvious. Along x, it will become x is equal to 0 to a. Along y axis, it will become y is equal to 0 to b. And for z axis, it will become z is equal to 0 to c. After having defined this, how will the Schrodinger equation look like in this case? Since the particle is moving in space in three dimensions, therefore, kinetic energy term or Hamiltonian will also have contributions from other two dimensions as well. Therefore, here the Schrodinger equation will become minus h square upon 8 pi square m del 2 by del x square plus del 2 by del y square plus del 2 by del z square. Potential energy is of course assumed to be 0 and that becomes equal to E psi. The total wave function for such a particle can be represented as the product of three wave functions, one along x direction, one along y direction and one along z direction. That means the total wave function is the product of these three wave functions. There is a justification for doing that because these components or these motions are independent of each other. And as you know that probability or wave function is ultimately through its square related to the probabilities, and probabilities of three independent events can be taken to be the product of the probability of each of these events. So there is a justification for taking this product. So wave functions will become multiplicative, but the corresponding energy, that means the total energy of a particle in a three-dimensional box, will be Ex plus Ey plus Ez. That means the total energy is additive, whereas wave function is multiplicative. If we substitute this in the Schrodinger equation, we get this expression. Now, if we simplify it further, as you can see here, we get three independent equations. One which is a function of x, another equation which is a function of y, and the third which is a function of z. So getting these three equations is very easy. So if these equations are quite independent and we have boundary conditions for each of these equations, then simplification and solution of these equations will give us both wave function for that dimension and the corresponding energy. You can see here that we get xx, that is the wave function along x direction, equals to 2 by a under root sine n x pi x upon a. It is similar to what we did earlier. Only thing is that here length of the box is replaced by a, and the corresponding energy is nx square upon into x square upon 8ma square. And similarly, we have the wave function for y and z dimensions, as you can see here, and the corresponding energies. So after having done this, one can find out the total energy as well as the total wave function for a particle in a three-dimensional box. Total energy, as you can see here, is E is equal to h square upon 8m, and in the parentheses we have nx square upon a square plus ny square upon b square plus nz square upon c square. So this gives us the total energy. And the total wave function psi, which is a function of three coordinates x, y, z, that if we multiply these three, it will be 2 by a under root sine nx pi x upon a. Then 2 by b under root sine ny pi y upon b. And then 2 upon c under root sine nz pi z upon c. So that's basically what we get. The wave function is further simplified if we assume the box to be a cube. That means if the three dimensions along x, y, z are equal, that means if a is equal to b is equal to c, then in that case, for a particle in a three-dimensional box having equal edges, that means in a cube will become equal to, the energy is h square upon 8ma square, nx square plus ny square plus nz square. And the corresponding energy, as you can see here, is psi xyz is equal to 8 upon 8 upon a cube under root sine nx pi x upon a sine ny pi y upon b. But again, instead of b, we will have a because all the edges are equal, and then sine nz pi z upon a. So this is the corresponding wave function for a particle in a cube of length a. Here you can see, when a particle is moving in a cube, an important concept can be illustrated, and that is the concept of degeneracy. For example, you see here that when nx square is 4, ny square is 1 and nz square is 1. In that case, the total energy will become equal to 6h square upon 8ma square. But this value of total energy can also be achieved when nx square is 1, ny square is 4 and nz square is 1, or when nx square is 1, ny square is 1, nz square is 4. That means there are three ways by which the same value of total energy can be achieved, and so on. Therefore, one can say that this system or system with this much energy will be having a triple degeneracy. This is very important concept. But when nx, ny, nz are all equal to 1, so there is only one way by which you can achieve the energy of 3h square upon 8ma square. That will be non-degenerate. So this way one can illustrate the concept of degeneracy by considering the particle in a cube. So in this module, we have studied today a very simple case of a particle in a box. First, we studied when the particle is in a one-dimensional box along x direction and the length of the box was L. We found that the total wave function for such that particle is 2 by L under root sine n pi x upon L, and the corresponding energy is n square h square upon 8 ml square. We also noted that in this energy expression n cannot be 0 because a microscopic particle can never be at rest, as it would violate Heisenberg uncertainty principle. Then we extended the case study and extended our studies to the particle in a three-dimensional box. We said that it is also very easy and we can separate the three dimensions x, y, z as they are independent of each other, and we calculated the total wave function as well as total energy. And lastly, if the three dimensions of a three-dimensional box are equal, that means if it is a cube, then the energy expression changes because A, B, C would be equal. That is what we considered, and the corresponding wave function will also get simplified. And from this, we also introduce the concept of degeneracy. That means different states which can have the same energy. So all this is very, very important in order to understand the concept of translational energy.